Hi, this is Nesniewski. The class is Discrete Structures. We're doing section 13.1. It's called Quantifiers and Predicates. Okay, so far we've been going in order. We're section 1.3, finished chapter 1, okay, and we did section 2.1 and 2.2. 2.1 and 2.2 was basic logic. Okay, the other sections of chapter 2 is more about logic, but they're also about proofs. And over the years I found that students just, when it comes to proofs, it's not a cookbook part of the course. It takes a certain amount of skill that takes years to get it right. So I skip proofs, but instead of proofs I do quantifiers, more on those quantifiers. So remember we talked about quantifiers for like 10 minutes, very little. We talked about for all x, p of x, and there exists x, p of x. Okay. What we're going to do now is we're going to skip to the last chapter, chapter 13, and we're going to talk more about quantifiers. It's a language that every technical paper or technical book in computer science uses. Okay, these quantifiers, and I think it's worthy of knowing about it. Okay, so let's back up a little and talk about what we're doing. Okay, beforehand we dealt with propositional calculus. Propositional calculus. Okay, proposition we said was a statement that's true or false. Okay, now we deal with something else called predicate calculus. Predicate calculus. Okay, so propositional calculus is things like P and Q and R. We dealt with that before. But now predicates, they don't talk about one thing, they talk about a whole class of things. Okay, they talk about a bunch of different types of things. The word calculus means how do you calculate with it, how do you do things with it, and so we're going to deal with it. But predicate calculus is about P of X, Q of X, Y, and Z, R of little a and little b. These are things or variables that denote things that we're talking about. Okay. Okay, so this is what predicate calculus is. Okay, and when you have such things, you can say how many of those things is this true for. So again, this is called a universal quantifier, and this is called an existential quantifier. The word quantifier means from the word quantity, how much. Okay, so this is showing you how much. We're going to do a lot of examples. The first examples we're going to do is somewhat fun. The next many examples we're going to do are more mathematical and exact. But we're just trying to get the lingo straight. Okay? Also, the book is very readable, and I don't do any problems that the book does. Okay, so that's true. Okay, first concept, we need a name. Okay, when we have a predicate P of X, you might say, first of all, what does it mean? But also, what are the X's? Are they numbers? Are they things? Are they people? So we have those. Whenever we're talking about predicate calculus like this, we're no longer talking, we're taking two sections off. We're not going to talk about propositionals. We're only talking about predicates. We have to have what's called a universe of discourse. Okay? In some other books it's called a domain of discourse. In other words, what are we chatting about? Are we talking about people? Are we talking about things? Are we talking about numbers? Are we talking about real numbers, natural numbers, etc., etc.? So whenever we talk about that, we have to deal with this. Okay, so for example, let's just do this. For all x, x squared is greater than or equal to x. Okay? Question, is this true? Okay? Okay, so, take 4 squared is 16, 16 is greater than 4, so that works for natural numbers. Okay? But what about all numbers? So here's the point. The question is, this statement, okay, so this is a predicate and it depends on x. It depends on x. It depends on x. And we can plug in a number here and we can see if it's true or if it's not true. Okay, what numbers are we plugging in? So it is true in the natural numbers. Let's just see. If for 0, 0 squared is greater than 0, that's true. 1 squared is 1, is greater than 1, that's true. 2 squared is 4, is greater than 2, that's true. 3 squared, etc., etc. 3 squared is 9, is greater than 3, it works. But let's say we're talking not about, let's say the universe of discourse is not the natural numbers, but the real numbers. Okay? The real numbers like this. Well, if you're talking about a number between 0 and 1, 0.5 squared is 0.25, okay, and that's not bigger than 0.5. So it's false over here, and therefore the fact that I'm saying it's true everywhere, universal discourse, no, it's not. All these numbers in between are a counterexample to this. So it's false in the real numbers. So the point is, it depends what you're talking about when you make a statement. What are the x's? Are they natural numbers or are they real numbers? Okay, good. Let's get into some, this is a more mathy statement, but let's get into some fun, non-mathy statements first. The book does this also, and you should read it. The book talks about m of x comma y, which means, this is what it means, the universe of discourse is people. Universe of discourse is people, okay, and mxy means x is the mother of y. Okay? Okay? So this is an example that the book does. We do another example. Love x, LXY, which stands for x loves y. Okay? And what we're going to do today is we're going to spend a lot of time writing formulas. Sorry, we're going to spend loves. This is loves. Writing formulas about such things and also about math and stuff like this. Okay, so great. So if this stands for x is a person, y is a person, and LXY stands for x loves y. So then what does for all x, for all y, LXY stand for? Okay? Anyways, and the answer is, it means for every person loves every other person. Okay? Every person loves every other person. So if we're talking about some group of people and they're in some type of utopia or some type of commune where everybody loves everybody and smoking, etc., this would be true. Okay? In general, it's not true. Okay? This, what about this? For all y, for all x, LXY. This says everybody is loved by everybody. Let's do this. This says everybody loves everybody else. This says everybody is loved by everybody else. Okay, now it's going to turn out that these two things are logically equivalent. Okay, we're going to see logically equivalent. We talked about logically equivalent. But let's talk about some other things. For example, for all x, there exists a y such that LXY. What does this mean? Okay, this says for every person there is someone such that LXY. So what that means is that everyone loves someone. Everyone loves someone. Okay, how about this? There exists a y such that for all x, LX, y. it's so bad to exist. Okay, what does this mean? Okay. Okay, this is a little bit more, this is different than this. This is not the same thing. This says, there is someone such that everyone loves that some person, that one person. Okay? There is someone that everyone loves that person. Okay? This says, for every person, there is someone that loves. So, for example, everybody loves their mother, right? So everybody has a mother. Okay, this is again part of utopia. Everyone is a person, and there is some person that is loved, that X loves that person. So in particular, you love your mother, you love your boyfriend, you love your girlfriend. Okay, everybody has different. It could be more than one person. Okay, this says something different. This says there is one person, there is at least one person, where there are some people, whatever, and everyone loves them. So you might say, oh look, everyone loves Mickey Mouse. Okay, so this is what that says. Here, for every X, there could be a different Y. Here, it says there is a Y that everyone loves. Okay, so they're two different things. Again, every person has a person that they love. By the way, every person loves themselves. Okay, so this is probably even true. This is not true. Not everybody loves Mickey Mouse or James Bond. Okay. Okay, so this says everyone loves someone. This says there is someone that everyone loves. Okay, it's a subtle difference. There's one person that everyone loves. Okay, how about this? There exists an X such that there exists a Y such that LXY. What does this say? This says there's got to be somebody in the world and another person in the world that loves them, such that the first person loves the second person. Okay, that's probably true. Okay, there's somebody in love with someone else. Okay, how about this one? This says, there is somebody who is loved by somebody. Okay? Now, let's go through. There is someone in the world who loves another person. So Archie loves Veronica. Well, this says there is somebody in the world who is loved by someone. So Veronica is loved by Archie. Turns out, if this is true, then this is true. If this is true, then this is true. These are logically equivalent. Okay. Okay. Let's do this. Okay, how about this? There exists an X such that for all Y, LXY. Okay? What does that say? There is somebody who loves everybody. Okay? They love everybody no matter what. Okay? So that's different than what we saw before. There exists an X such that there exists a Y. There exists an X such that there exists a Y. That says everybody has somebody that they love. Oh, I'm sorry, that says there is one person who loves somebody. This says there is a person who loves everyone. So, I don't know, Mother Teresa, okay? She takes care of all sick people. She loves everybody. How about this? We did this for all X. Yeah, for all X there exists a Y. We did this. Every person loves somebody. I said, everybody loves their mother. How about this? For all Y, there exists an X such that L of X comma Y. I'll erase this because this we dealt with before. Okay? This is the same thing as this, but we switched the thing. What does this say? This says, for every person, there's someone who loves them. Now this is true. Okay? No matter who you are in life, your mother loves you. Okay, you can be a mass murderer, you can be Jeffrey Dahmer, your mother's going to come visit you and tell you, oh, you sweet little boy. So every person has someone who loves them. No matter how bad you could, as a parent I could say, no matter what you do to your parents, they still love you. Okay, but it's different than this. This is what this says. This says there is some person that loves everyone. This says for every person there's someone who loves them. So Mother Teresa would satisfy this thing. Okay, she's one person who loves everybody. This says for every person there is someone who loves them. Now we're going to see later on, in fact, that this implies this. Let's go through why. If Mother Teresa loves you, it loves everybody, then for every person, the person who loves them is Mother Teresa. But it doesn't go that way. Okay, let's say Mother Teresa's dead now. This statement is still true. This statement is false. There's no person like Mother Teresa who loves everybody, but this statement is true. This says, for every person there's someone who loves them. Yeah, your mother loves you, your father loves you. Go make nice to your father. Okay. Okay, now for a song, what does this mean? This is the lyrics of a song. Okay. It says, can you be loved? Will you accept, does there exist a person that will love you? Okay, this is what every teenage boy and girl thinks about. Okay, let's do this. This is the plot of 90% of all romantic comedies. See what it says. It says, well, maybe it should be there exists. There exists an X, so this is a romantic comedy. Ready? There's a boy, there's a girl, there's a boy or a girl, there's somebody, and there's another person. And X loves Y, and Y does not love X. That's called all of literature is this unrequited love. When someone loves you and you don't love them back, or you love someone and they don't love you back. Okay, that's where the pain in the universe happens. Okay, so we'll have a lot of fun with these things. Okay, let's do some more mathy examples. Okay, how about this? For all X, for all Y, there exists a Z such that Z equals Y minus X. Now this is a predicate, so we can say this, pre-X, Y, Z is equal to this thing. Okay, question, is this true? For every number X and number Y, there is a Z such that Z is equal to Y minus X. Is this true or is this false? And the answer is, just like before, it depends. Okay, this is false in the natural numbers. Why? Okay, because in the natural numbers, yes, it's true 7 minus 5 is equal to 2, but what about 5 minus 8? That's negative 3. 5 minus 8 is negative 3. That's not in this universe of discourse. Okay? However, it is true in Z. This is positive and negative numbers. Okay, so let's see this. Take any positive or negative number. Take another positive or negative number. Subtract them. Is that a positive or negative number? And the answer is yes. So it works for Z. Doesn't work for this because this only has positive numbers. Okay, so this is a predicate. I didn't write it as a predicate, but that's a predicate. It's called a three-place predicate. Okay, now let's do another thing. What about this? For all y, p of x comma y comma z. Let's just forget about it. I'm not talking about this. We're finished with this. That's a nice example. We worked it out. Very nice. Let's just talk about this. We have a predicate with three things. Okay? Now, this is a statement that depends on x and it depends on y. This could be, it depends on x. You plug in a number for x, you plug in a number for y, or you plug in something for x and y. I'm sorry, for z, x and z, and it's either true or false. Okay. Now we separate variables. Okay, y is called a bound variable. That means I've bounded. This takes care of this y, and it says, look, I'm assuming that I'm going to use this y as the predicate, so it's either true or false. Okay, x and z are free. They're not bound. They're free variables. Okay, and you can plug in values for x and z. Okay, and when we did this for all x, for all y, there exists a z. Okay, of q of x comma y comma z, then all three of them are bound. All three of them are bound. You have a quantifier binding. It's saying, oh no, you can't move these around. I'm saying this is for all that exist, etc., etc. Okay, so let's just say this. For all y, p of x comma y comma z, this is a predicate of two variables. There are two variables, x and z. Okay, you plug in different values for x and z. Great. Now, okay, now I'm simply going to go through 5 problems. 1, 2, 3, 4. A few problems from the not from the homework, from the book, and we'll do it together. Okay, and then we'll do the homework. Then there'll be homework problems. Okay, so basically, I don't do any problems that the book does, so you can read what the book does. We're going to do some of the problems in class from the back of the book. We're going to leave the other ones for homework, and of course, not all the problems in the homework. That I need for tests. So if you want to really know this stuff, you study every problem in the book. Okay, so let's look at problem 3E in the book. This is problem 3E. Okay, and we're talking, the universal discourse is the natural numbers. Okay, and we have the following statement. For all m, for all n, it is false that 2n is equal to m. Okay, I could write it another way. Let's write it another way. For all m, for all n, 2n is not equal to m. Okay? We want to know, is this true or is this false? Okay? Now, how do you make, this is a universal statement. This says every m and every n. How do you make this false? How do you make it true? Well, to true, you have to see that it's true all over. How do you make it false? You just have to find one counterexample. So look what it says. Every m is equal to, for every m and every n, there is 2m is not equal to n. Okay? Anyways, it's false. Okay? Let's say m is equal to, I don't know, 14. N is equal to 7. 2 times 7 is equal to 14. So don't tell me they're never equal. Sometimes they are. So it's false. Obviously, sometimes they are true. For example, m is equal to 14 and n is equal to 8. 2 times 8 is not 2 times 8 is not equal to 14. So in that case, this would be true. But we have one counterexample. We have many of these. I have an infinite number of counterexamples, but this is a counterexample, and therefore it shows that this universal quantifier, the counterexamples are enemies of universal quantifiers, is false. Okay, great. Okay, let's do another problem. 4e. Okay. Okay, we're talking about in the real numbers. Okay, let's see what it says. For all x, there exists a y such that x plus y squared is equal to x squared plus y squared. Okay, now let me just go over here and let me tell you what most students who didn't have a good high school education think. They think x plus y squared is equal to x squared plus y squared, but that's not true. X plus y squared is equal to x squared plus 2xy plus y squared. Okay, you have to do FOIL. Great. Question, when is this true? Okay, is this true? Okay. Let's see what it says. It says for all x, there is some y such that this is true. Okay, we're talking about the real numbers. And is it true or is it false? Okay, you have to think about it for a minute. And you say, but the answer is it is true. It is true. Okay, when is it true? When does there, give me the y that this exists for. And the answer is x plus 0 squared is equal to x squared plus 0 squared. So since this is in your number, 0 is in your domain of discourse, it is true. For all x, give me any x whatsoever, x plus 0 squared is equal to x squared plus 0 squared. So it works. Okay, what about there exists a y such that for all x, x plus y squared is equal to x squared plus y squared? And the answer is yes, it is true, because if this is true, this is also true. And the answer is, what number, when you add it to any x, x plus y, and the answer is x is equal to 0. Both of them, x is equal to 0. This is true when x is equal to 0, this is true when x is equal to 0. Okay. In general, and we're going to see this more in next section, in general, whenever you have exists a y such that for all x, p of x comma y, this implies for all x, there exists a y, p of x comma y. This goes one way. This logically implies this way. It does not logically imply this way. Something could be true here and not true here. Okay? Let me show you an example of this. Okay? You ready? We're dealing in the real numbers. Okay? This is not a problem right now. So right now we're just proving this. So we're talking about the real numbers. How about this? For all x, there exists a y such that x plus y is equal to 0. Okay? That's one statement. Now another statement. There exists a y such that for all x, x plus y is equal to 0. Okay. Notice the formulas are exactly the same. The variables are the same, x and y. The quantifiers are the same for all x, for all x. There exists a y, there exists a y. The only thing that's different is the order of the quantifiers. Let's see what this says. This says, give me any number whatsoever. There's a number that when you add it you get 0. This says there is a number that for any number when you add it you get 0. Okay? Well, turns out, let's pick a number, 13. What number should you add to 13 to get 0? Answer, negative 13. Let's try another number, 45, or 45.8. Well, how about minus 45.8? When you add 45.8 plus minus 45.8, you get an S. So this is true. Okay, what about this? Is this true? Is there some number y such that no matter what you add to it, you get 0? Okay, for any number. And the answer here is false. I'm sorry, I wrote this the wrong way. Anyways, so we see this implies this. False implies true. But more important, if this was true, then that would definitely be true. Let me show you an example where this would be true. How about this? There exists a y such that for all x, x times y equals 0. Not plus, but times. Question, is there some number y such that when you multiply it by anything, it's 0? And the answer is yes. Y equals 0. Let's do the other side. You ready? For all x, there exists a y such that x times y is equal to 0. Is this true? And the answer is yes, it is. Take any number, the number 0 works. So y is equal to 0. X times anything, 0 times anything is equal to 0. Perfect. So here we see again, this is true, and it implies this is true. And in fact, the answer to this can be used here. Okay, great. Let's do some more. Okay, 5F. Okay, 5F says the following. Okay. For every n member of n, there exists an m such that 2 to the m is less than n, and n is less than 2 to the m plus 1. So let's write it. For every n, there exists an m such that 2 to the m is less than n, and n is less than 2 to the m plus 1. Okay? Okay, so that's a statement of it. Okay? And let's just think about it. Take the number 10. Okay? 10 is between the following two powers. 8, which is 2 to the third, and 16, which is 2 to the fourth. So the number 10 is between these two powers. Okay, and any number whatsoever, pick a number, 25. 25 is less than, let's see, what's 16 and 32. This is 2 to the fourth, and this is 2 to the fifth. Okay, so it seems to be true, but just remember this is for all n. There's one number where it's false. Okay, let's do it for 1. 1, oops, I'm sorry, I left out this. Okay, 1 is less than 2 to the 0, which is less than 2 to the 1. So this 2 to the 0 less than or equal to. So this 2 to the 0 is 1. So 1 is equal to 1. Like that. So it really works for almost every number. The only thing is we said that this is a part of n. Okay? It fails for 0. Therefore, it's false. Okay? Okay, so that takes care of that. Okay, great. Okay, one more problem, and then we'll call it quits. 15D. Let's just read it. 15D. If f goes from A to B such that A is a member of A, there is exactly one B such that f of A is equal to B. Okay? Okay, so for all f, you know what, let's leave that out because that's not really part of our universe. Okay? So f goes from A to B. Okay? D. For all A member of A, there exists a B member of B such that f of A equals B. Okay. By the way, what does this mean? This means for every A there's a B. That's true. Okay? That's what the definition of a function is. But now we have a new quantifier. So let's remember quantifiers. We had a quantifier for all of x, p of x. We had which means every single x it's true. We had a quantifier for there exists an x, p of x. And now we have a new quantifier. It's called unique p of x. That says this is true for exactly one x. This means for one or more, but this says this says there is some. This says there is one. Okay, so now let's change this. Okay, for all A, there exists one B, such that f of so I'm sorry. This is not the definition of a function, because this could be more than one B. Okay, so you could have right. You can have more than one B. So that's not. This is the definition of a function. For every A, there is a B. Okay, great. Now let's go further. How about this? So this is a function. That's the definition of a function. What about this? There exists a B. No, sorry. For all B, there exists an A such that f of A equals B. Look what this says. This says onto. What does onto mean? It means everything in here, here's A, here's B, everything in here is hit. So look what it says. For all B, every guy in here, there is an A, there is a guy in here, such that f of A is equal to B. Okay, now let's do this. For all B, there exists a unique A, such that f of A is equal to B. What about that? Well, this says not only is it onto, but there's only one A that hits this. You're not going to have something like that. Two different A's, A and A prime, that go to the same B. Okay, so this is onto and one-to-one. Okay, so that's a one-to-one correspondence. Okay, anyways, lots of fun writing these different statements in English, making them into symbols. Okay, that's what we did today. Okay, the way to get this is a language. There's nothing complicated about it. It's a language that you have to learn to do it. The way to do it is do the homework problems. Do the homework problems, and then we'll do the homework problems together. Okay, take care.